Okay, very first, okay, the mic is on. You can hear me? All right. Okay. So I hope you all had a good lunch. I hope you're invigorated, ready for the, can you hear me? Okay. Do I need to move it up a little bit? Is that better? Okay. So I hope that you're all invigorated, ready for the afternoon's talks. I'm Rachel Osten. I am a stellar astronomer at the Space Telescope Science Institute. For those of you who are tweeting, you can tweet hopefully only positive things about what you're going to hear today. This is going to be a very different talk than the two lectures that you've already sat through. I have the sort of unenviable position of going from, you've heard a talk on an overview of global processes that's very theoretically motivated, lots of equations. The flavor of this talk is going to be, and now for something completely different. So I'm going to be talking about using stars to understand processes that are happening on the sun through the perspective of time, evolutionary time. So before I begin and before I forget, there is homework. You can peruse this while I'm talking. That out. You can distribute back that way. Oh, all right, thank you. And for this table. We'll discuss these questions tomorrow during the homework section. But you can be looking at them while I'm talking and thinking about how to answer some of the questions. First I want to tell you what I'm not going to talk about. I'm not going to be talking about general stellar activity. Carol Shriver tomorrow is going to give you a lecture on observations of stellar dynamos. Paul Charbonneau next week is going to talk to you about dynamos in more detail. I'm going to be talking about, I'm not going to be talking about solar flares even, I'm going to be talking about stellar flares, so it's a very specific topic. I want to give you a general overview of what we know about stellar flares through the lens of time, but taking into account the rather large parameter space that we have available to us when we move away from just studying the sun to considering other stars. And so I'm going to try to make sure that I explain the astronomy terms for those of you who maybe haven't had as much of a background into the astronomy or for whom some of these concepts might be a little vague. I'm also going to ask you questions, so they're not going to be very hard, I promise. But just to make sure that we're all on the same page and we're all understanding the same terminology. And I've broken up the lectures, if I've timed this right, and I haven't actually timed it, so I don't know if this is going to work, but I have two different lectures. The first one is going to talk generally about flares. I want to describe a little bit the kinds of processes that are occurring when you study flares in different regions of the electromagnetic spectrum, what kind of information you can get. And then in the second lecture, I'll go into synthesizing studies of stellar flares from the perspective of on evolutionary timescales and what we might be able to understand about what our sun might have done in the past, what other types of stars that might be harboring planets and solar systems might be experiencing. Okay. All right. So I like to start with this quote. It's humorous, and this is a nice touching point off the very nice introduction to heliophysics this morning. And I particularly like this when I give a talk to a mostly astronomy community because there's a lot more truth to this statement than I would really honestly care to admit. But okay, so the sun's magnetic field is what makes it interesting to astronomers, to me, the fact that the sun is a dynamic environment with this magnetic field that you can see nicely illustrated in this trace image of solar coronal loops. And the title of the chapter and the title of the talks are Stellar Explosive Events Throughout the Evolution of the Solar System. So the explosive event is a term that is very all-encompassing. This is an artist's conception of what a flare might look like on the sun, by the way. It's not an observation. It involves particle acceleration, plasma heating, and mass motion, so there's a number of different physical processes involved. Happens as a result of magnetic reconnection, so there's the first reference to reconnection that Tomas promised in his lecture this morning. It involves all layers of the atmosphere, from the photosphere through the chromosphere and into the corona, even into the heliosphere, as some of you are much more expert at that component than I am. Produces emissions across the electromagnetic spectrum and has different components. There's a flare, the coronal mass ejection, the solar energetic particles. An important point to remember for the rest of this talk, actually, is that when we stellar astronomers talk about these eruptive events or explosive events, what we observe is the radiative manifestation of that. We observe the flare. I'll talk about this in a little more detail. But all of these processes that are occurring, we can only really investigate one component of that in detail. That's the flare. That's what we have observational constraints on. Okay. There's already been a reference to the Carrington event, which was the first solar flare that was identified in white light observations. I thought this was interesting. This is mostly a historical note. This is the first recorded observation of a stellar flare by this guy, Einar Hertzsprung, who hopefully everyone is familiar with. Who is his compatriot? Russell, right. The Hertzsprung-Russell diagram. That's like the foundation point of understanding stars. So it turns out he wrote a lot of papers that had this title, on a note on a peculiar variable star or nova of short duration. But in this case, the star that he is actually observing we now know to be a flare star. So he observed a flare on this star sort of serendipitously. So I'm going to start with a number of just assumptions, statements that we can explore as we get into describing stellar flares and comparing them with what we know about solar flares and trying to think about extrapolating backward in time or to different parameter regimes. But I'm going to start with the assumption that since we see many commonalities with solar flares on stellar flares, that tells us that there's the same physical mechanism that's occurring. And that enables us to take the large body of observations that we have on stellar flares, which are varied in stellar age, stellar mass, stellar rotation, and other parameters, and use those, turn those around to try to understand what the sun might have been like. But that's an open question, and we actually need to do detailed studies of these stellar flares to confirm that yes, it looks like the solar analogy does hold, or where there are other instances where it looks like it doesn't hold. So even though we have only one star, we can try to broaden that by looking to other stars. And there's we don't study other stars in the same detail that we study the sun, so there are necessarily limitations. Okay. I want to give you a flavor of the kinds of flares I'm going to be talking about. And I'm going to use a couple of very simple ways to think about flares. There's the maximum duration, and then the intensity increase in two different wavelength regions, in the visible and in the X-ray. So on the sun, you've got large flares releasing about 10 to the 32 ergs, maximum duration 5 hours, tiny, tiny increase in intensity in the visible, and factors of a few thousand for the largest X-ray flares compared to the underlying quiescent emission. And if you look at these other rows for very young stars, single stars, and binary stars, you can see that by and large, these numbers are much larger. And that's sort of an observational constraint, that because we're looking at stars that are not the sun, that are much further away, we're necessarily limited by the 1/distance squared restriction that we can only see these very intense events. Yep?
So I'm curious, is the single stars, are we still talking about G stars, or is there a specific type? And with the binary stars, are they interacting, or are they far apart?
Those are very good questions. So, so you asked if the single stars were referring to G stars or some other kind of stellar type, and if the binary stars are referring to stars that are interacting or not. I'll answer those questions in the next slide or two.
Those numbers are all like upper limits.
No, they're not upper limits. Those are measurements.
Those like typical numbers for.
Oh, okay. So yeah. So are these numbers typical numbers, or are they extremes? These numbers are extremes. Okay. So I want to set, even though I said I wasn't going to talk about activity in general, I want to set a little bit of a groundwork for what we mean by magnetic activity, since flares are one aspect of magnetic activity. So this is a pretty familiar diagram of the internal state of the sun, and then some of the magnetic phenomena that we see on the surface of the sun. And pretty much all of these things that you see on the surface and above the visible surface of the sun happen as a result of the presence and action of magnetic fields. And we know that the sun is what kind of a star is the sun? A G2. Okay, what's its temperature? 6,000 degrees. Okay. So for a star that's on the main sequence, that's a G2 with a temperature of 6,000 degrees, it has an internal structure that has a core where the nuclear reactions are taking place that are powering the sunlight. That energy is transported by radiation in the inner 70% of the sun by radius, and then in the outer 30%, the energy transport mechanism switches over to convection. How the sun is able to produce its magnetic field is a topic that I'm going to leave for someone like Carol or Paul Charbonneau to address in their lectures on dynamo processes. But we know that when stars have an outer convection zone, they are magnetically active. They can be magnetically active. For stars on the main sequence, that occurs for stars that are just slightly more massive than the sun, all the way down to things that aren't even stars anymore, that are brown dwarfs. So this activity sort of correlates in a broad sense with these two parameters, convection and mass, which are correlated with each other. There's another two parameters that also are important in activity, and that's age and rotation, which also are correlated with each other. So this is a plot from a paper by Tom Ayers showing observed spread of rotation speeds on clusters of different ages. And you can see that these stars start out rotating very rapidly, and then they decay with time. This is a well-known relationship called the Szymanich law, because this is approximately a power law of t to the minus 1/2. So these stars, they have a lot of angular momentum when they're young. They experience magnetic braking, and they slow down with time. Here's another plot of this showing the X-ray luminosity of the star, G stars versus age for stars that have well-known ages. Okay, so that's the activity-age relationship. But rotation and age are correlated with each other because I just showed you that stars rotate faster when they're younger. This is an example of stars that are very active. This is a close binary of two nearly solar-like stars that have orbital and rotational periods of a little over a day compared to the sun's rotation period, which is 27, 28 days. So this is rotating much faster than the sun is, the single sun. These two stars are not exchanging mass, so that gets to the question that was asked before about the flares on binaries. But because they're so close, they're tidally locked, and they rotate much faster than they would if they were single stars. In fact, these kinds of binaries can maintain extreme levels of activity at very old ages compared to single stars. So age and rotation are degenerate with each other in this case. There is a more fundamental parameter that correlates with activity, and that's called the Rossby number. I'm not really going to go into a whole lot of detail on what this is. It's the ratio of the rotation period of the star to the time scale for convective turnover at the base of the convection zone. So this takes into account how fast the star is rotating. It also takes into account the evolutionary state of the star, not the evolutionary state, the mass of the star. So stars that are sun-like or more massive than the sun have thin outer convection zones. As you go towards less and less massive stars, the convection zone deepens until you get to stars that have a mass of about a third the mass of the sun. Those stars are completely convective. Those stars fall in the M dwarf range. In another phenomenon that I'll point out here, but won't really go into a lot of detail, is this. You can see from looking at this plot that there looks like there's three regimes here. You have this nice regime here where the X-ray, the activity is decaying roughly as the Rossby number to the -2 power. You've got this level here, which is roughly flat. It's about a little below 10 to the -3 in Lx over L Bowl. And then in these very fast rotating objects with very low Rossby numbers, you can see that this X-ray emission is actually turning around. So these stars are called unsaturated. These ones are saturated. These in quiescence, so when the star is not flaring, these measurements are made when the star is not flaring, they seem to be able to maintain a level of X-ray emission that's about 0.1% of their underlying bolometric luminosity across a range of different bolometric luminosities, stellar bolometric luminosities. And then over here, for these objects, they appear to be undergoing something called supersaturation. So these stars are saturated, these ones are supersaturated. So there's something is happening so that their coronal structures or coronal heating that's occurring in these stars, perhaps because of their fast rotation or some combination of rotation and convection, they're not able to maintain coronae that are as bright as these other coronae.
Rachel, I want
to
point out where the sun is in this diagram.
That's a good question. I don't actually know where it is.
Lower right.
Lower, it's over here.
At a LX or L Bowl about -6 or
Yep.
-6.5. So right near the bottom.
Yeah.
Interesting, the X-ray luminosity can characterize the level of stellar.
Yes.
Repeat.
Oh, all right. So the question is, can the X-ray luminosity relative to the bolometric luminosity of the star be used to characterize the level of the star's activity?
Why is that?
Why? So why can the X-ray emission be used to characterize the star's activity? So the coronal emission from stars is produced as a result of the influence of the magnetic fields. So the intensity of the X-ray emission is going to be proportional to the amount of coronal heating that's occurring in that star.
That's quiescent, not the...
That's quiescent, yeah.
So now we're talking about activity.
This is quiescent activity.
Oh.
So this is a plot that is meant to demonstrate that convection and rotation are actually linked in discussing activity. This is not just convection zone depth or mass. It's actually the product of those two. But when we talk about flares, we're going to be in regimes where the star's X-ray luminosity can exceed this value on short time scales. So this is just an overall way of characterizing the level of coronal heating that's occurring in these stars and whether they're active stars or inactive stars based on their underlying X-ray emission. Is there a question? Another question?
Can you say a little bit about these solar-like stars? In which talking about exactly? Only G-type stars, or are we moving away a little bit of it?
Okay, so the question was, what do we mean when we say solar-like stars in the context of this plot? So observationally, the sun has an LX over L bowl that's about 10 to the minus 6. And I don't happen to know what the Rossby number of the sun is off the top of my head, but
It's basically on that straight line going down to the lower right, the sun is at the bottom of that line.
yeah. So we can measure the rotation rate of the sun. We have some constraints on what its convective turnover time is. So we can put the sun. So in this sense, sun-like stars, a sun-like star would be something with LX over L bowl and Rossby number, similar to what the sun has. But that's actually a good question because sun-like can mean different things to different people. It's sort of akin to astronomers of different flavors using low-mass stars, which can often imply a factor of 10 difference in mass. Yep?
In this graphic is showing log Lx to log R0 for all the sun-like stars which have the same chemical composition.
This is
when you say
this is the X-ray luminosity to bolometric luminosity for main sequence stars, so not sun-like stars, not.
solar-like stars activity. Okay.
So when I say so in this reference, solar-like stars, I'm talking about stars on the main sequence, for which I showed you previously this onion skin diagram of the sun. And we talked about how higher mass stars on the main sequence have thinner convection zones. Right. Okay, and then lastly, as you might expect, for stars where you can measure the magnetic field in the photosphere, and you can measure the surface X-ray flux from the star, those two things are correlated. Since we think that since we know that the X-ray flux or luminosity from the star is produced as the result of the action of magnetic fields and magnetic heating. Okay. So that leads us to getting back into talking about flares on different kinds of stars. And there is a definite bias that exists in the kinds of information that we know about stellar flares as distinct from solar flares. And this gets to the question that was asked earlier about what do we mean by binaries and single stars. I'm going to categorize them in 3 groups of stars that are typically targeted for flare studies, for in-depth studies of their flares, as opposed to just serendipitous measurements of flares. The first category are young stars. So we mentioned that young stars are active because they're rotating rapidly. So they show signatures of enhanced magnetic activity, both in a quiescent sense, but also in flaring. Young stars are interesting, but they're also they can be a little bit problematic in studying and interpreting. And that's because young stars still retain some of the signatures of their formation, and they might be actually engaged in the active process of forming planets. So this is a schematic of a young star that we would call a class 2 star. This star still has a disk around it, which you can see out here. That disk might be forming planets. And it's active. It has, this is an artist's conception, of course, but it has coronal loops that could be quite small, on the size of the solar coronal loops. But they could also have large coronal loops that could, in theory, connect the star to the planet-forming disk. And that introduces a lot of additional physics, additional complications to understanding and interpreting flares from these stars. But they're young, they're very active, they're flaring frequently.
Those large X-ray coronal loops part of the quiescent X-ray luminosity, or is short duration?
Okay, so the question was whether these large X-ray loops are part of the quiescent X-ray luminosity of the star, or whether they're only occur during flares. I'll talk about this in a little more detail when I get to. Actually, it might be in the second talk. But we only really have evidence for these during flares. There are other ways to interpret. So since we can't resolve these stars, we have to use indirect methods to try to determine what a length scale might be. The second type of star that's typically targeted for flare studies are active binaries. This is a schematic showing a possible configuration for two magnetically active stars where you have the magnetospheres of the two stars interacting. I showed you an example before of two solar-like stars that had a very enhanced rotation rate because they're tidally locked. These stars are also show enhanced levels of flaring. They show extreme flares, as I showed you in the table earlier. So these flares can be up to 10 to the 36 or 10 to the 37 ergs, 10,000 to 100,000 times more energetic than the largest solar flare.
Is it possible that one of the stars can be like hot Jupiter, because hot Jupiter also have a huge magnetism?
So the question is, could the same configuration apply to a star with a hot Jupiter that has a magnetic field, where you could have the magnetospheres of the star and the planet interacting? Yeah, I mean, it's the key point in these active binaries is that they're rotating very rapidly. As I mentioned before, there's this rotation-activity relationship. So if you have a star that's rotating rapidly, it could be because it's a very young star, a single young star. It could be because it's part of a tidally locked system that's rotating rapidly because of that gravitational influence. So yeah, so if you have a hot Jupiter that can enforce tidal locking in the system that's experiencing that, I wouldn't rule that out, and that's been suggested by other people.
Are there any observation methods of that kind of system producing flares?
There have been speculations that planets have stimulated flares on their parent star. Okay, and then the third category of stars that are typically targeted for flare studies are the single, fully convective M dwarfs. And so this is the category of single stars that I was referring to in that table. It turns out that these M dwarfs, which are they're puny little stars. They have maybe a third the mass and a third the radius of the sun, and yet they're able to produce these extreme outbursts. This is an artist's conception of one of them. I'll show you some examples later on. Their flares seen in the optical are characterized by increases of up to factors of 1,000 over the underlying stellar luminosity. And in the X-ray, the coronal radiation from these flares can be up to several thousand times the underlying stellar luminosity. So if you remember, what did I say the saturation level for stars was when they're not flaring? It was Lx, the X-ray luminosity, to the bolometric luminosity of 10 to the minus 3. So if these flares can get several thousand times brighter, what does that imply? Yes, the X, so if Lx over L bol in quiescence is 0.001, and in the flare for a short period of time, the X-ray luminosity increases by factors of several thousand. That means that for a brief period of time on these M dwarfs, the flare outshines the star. Another way of putting that is that the star increases its bolometric luminosity on timescales, not evolutionary timescales of millions or billions of years, but on the timescale of 5 minutes or 10 minutes. And it's magnetically powered. Okay. This is a plot that's just designed to give you a flavor of the different kinds of stars where we see flares. And I'm going to concentrate on flares that are observed on main sequence stars to kind of cut down a little bit on parameter space. So this is an F dwarf, so it has a very thin outer convection zone, and you can see this flare here observed in the extreme ultraviolet. This is an active evolved star, single evolved star. Here's another single evolved star that we think may be the remnant of a binary system where the orbital evolution of the two stars proceeded such that this star ate its companion. So we see this to be a rapidly rotating single supergiant because of the end product of that magnetic activity. Nick, did you have a question? Oh, okay. Oh, yeah, it's a little washed out.
So axis is,
So this is the...
all of them are on the same type of axis?
So that they are, time is on the x-axis and count rate or luminosity is on the y-axis. So I apologize for that. So maybe it was just concentrate on the different types of stars that were called out here. So here's a young star in the Orion Nebula cluster. Here's this.
What's the trace on that look like?
Sorry?
What does the trace? What does the data look like? Is there a peak on that?
Yeah, this might be better viewed from your laptops if you can go in through the NCAR, UCAR site to pull up the slides.
Are you going to talk about the decay of these flares, the actual shape of the flares?
I'm going to talk, in this talk, I'm going to break it up into different wavelength regimes. So I'll show what we can study about flares in the radio and the X-ray. So if by decay you mean a specific phenomenon, I'll address that somewhat perhaps in some of those wavelength-specific regimes. So yeah.
How do these flares compare to S flares or these X?
Yeah. So that table that I had at the beginning of the talk tried to give a sense of some of the extremes of these flares compared to solar flares. If you take the largest of those flares and try to put them on the same scale as solar flares, then you get X. The largest ones would be like X 3 million flares in terms of their luminosity. So yeah, so like I said, they're big flares. And so let's see, I wanted to go. There was one other point I wanted to make about this slide. So if I just go back to this briefly. Where does the sun fit on this? It doesn't. Why not? Why does the sun not fit on this?
Not fully connected.
Okay, so it's a single star. It's a G dwarf. It's relatively old. So that immediately tells you that there's a disconnect in the types of stars that we know a lot about for flares. So if you looked at your homework, then you can already begin to start thinking about the first question. So when we think about stellar flares and the kinds of processes that we can observe in stellar flares compared to what we see in solar flares, if you use a holistic approach, this is Boulder, so we're all into being holistic and natural and everything. So we actually find pretty good agreement in the manifestations of stellar flares that correspond with observational signatures that we see on the sun. And there's a couple of exceptions here. We've got radio gyrosynchrotron emission from accelerated particles, which we see in the sun. Solar flares, we also see that during stellar flares. These accelerated particles produce signatures of non-thermal hard X-ray emission in solar flares. We may have seen that in one stellar flare. I'll describe a little bit why that's a difficult measurement to make. Coherent radio emission, these are plasma processes, wave-wave interactions, are seen in the sun. There's a whole diversity of these phenomena in the sun during solar flares, and we also see those in stellar flares. The transition region of the sun and of stars, I'll describe a little bit what the transition region is for those of you who don't, for whom that statement doesn't mean anything. So this is plasma that has a temperature of about 100,000 degrees, more or less. The transition region is the part of the atmosphere where the plasma switches from being controlled by the gas to the magnetic field controlling motions. In the corona, the magnetic field dominates. In the chromosphere and below, the gas motions dominate. In the photosphere, the visible surface of the star, we also see evidence for solar flares. This originates in the optical and UV. Coronal mass ejections. We do not have any confirmed observations of stellar coronal mass ejections. Ofer Cohen is going to tell you later on about taking what we know about the sun and trying to apply it to some of these very active stars to see what these stellar coronal mass ejections might look like. But we don't actually have any observational constraints on them. Same thing for energetic particles. X-ray emission, we have ubiquitous signatures of stellar flares, and chromospheric emission, we also have ubiquitous signatures of stellar flares. And I should mention that these check marks are made by looking at different types of stars. So because of the limitations of studying one particular star and studying it in depth, we can't put these check marks just by looking at one star. But if you look at an ensemble of flares across many different kinds of stars, you see all of these. And even within different classes of stars, there are commonalities there. So that's how I'm able to put these check marks on, even though we don't necessarily have one stellar flare that's shown all of these signatures in that one particular event. And this slide is mostly for reference. This is just from the astronomical point of view, the types of instruments that we use when we do stellar flare observations, the wavelength ranges, the names of some of these instruments. Many of these are archival, and what kinds of information you can get. I won't read all of these off. You can look at them, but just we have access to a pretty large span of the electromagnetic spectrum by using these different instruments: space-based instruments, ground-based instruments, radio telescopes, optical telescopes, UV telescopes, X-ray telescopes. Okay. How am I doing on time? Okay, to the middle of the first talk, or? Through the bright, oh, okay, all right, I'm not talking fast enough. So the Newport effect is our standard interpretation of what we think is happening during these stellar flares that we've seen on the sun in solar flares, and gives us some observational signatures that we can look for when we're studying stellar flares. That is one of those key pieces of evidence that tells us that we think we're seeing the same process in these stellar flares as we see on the sun during solar flares. So it starts with magnetic reconnection. That reconnection, the liberated energy goes into accelerating particles, which travel down field lines, produce gyrosynchrotron emission. Some of those particles are trapped, producing gyrosynchrotron emission. The ones that precipitate from the magnetic trap produce hard X-ray emission when they encounter the dense chromosphere. That material becomes heated on timescales short compared with the hydrodynamic expansion time, and it undergoes an evaporation, which produces a soft X-ray emission that you see as a flare. So there's a natural sequence of events that you expect to see in this scenario. This is an observation of the Newport effect on the sun. So the purple curve is the X-ray flare. The red curve is a millimeter flare. The orange curve is a centimeter wavelength burst, and green is a hard X-ray burst.
Is this the same physics that we use with sun?
Yeah, so is this the same physics that is happening on the sun during solar flares? Yes, that's the assumption. This is an example of the Newport effect on the sun during a solar flare. This plot over here is an example of the Newport effect seen in an M dwarf flare on an M dwarf, where you're seeing the extreme ultraviolet response of the flare, and the curve is the optical emission from the flare. And I'll just kind of go through these quickly. These are examples of the Newport effect seen in different wavelength regions on different stars. So here's another M dwarf where we see a radio flare, and you can see an X-ray flare here. This is an active binary system, same thing. There's a radio flare, there's an X-ray flare. They're in more or less agreement with each other using this Newport effect interpretation. And that interpretation allows us to go into other regions and find that expected integral relationship between signatures of non-thermal particles in the flare and signatures of the response of thermal plasma heating. So in this flare, another flare on an M dwarf, you've got the X-ray light curve, you've got an optical light curve that seems to match. The flare on the right is an example of the Newport effect between hard X-ray photons and soft X-ray photons. Okay. And I think at this point it's probably good to take a short break, and then I'll have to speed up a little bit to get through the description of the wavelength ranges and then go on to how things vary with time. So my watch says it's almost 2 o'clock, so I'm going to take a 10, 15-minute break. 10? 15? Okay. Yeah.